Motional EMF. We've already met the basic situation shown in the figure. In our case now, a metal bar is sliding along at constant speed v due to an applied external force F. The magnetic field is directed out of the page and is constant. Note that there is a resistor R in the loop. Mark the dimensions of the loop area as x and L, where x is the horizontal base of the rectangle and L is the vertical height. So x is right there, and L is that right there. Recall that velocity is the time derivative of something. Figure out what that something is, and next to v in the figure, write d something dt. Velocity, we recall, is dx dt. So we've got that. As the bar slides, circle the direction of the induced electric field, induced EMF, and the induced current. So the bar is sliding this way, which says what? The flux is directed out of the page. As it slides to the right, there will be more flux out of the page. And according to Lenz's law, we don't like change. I don't like that increase in flux. So I'm going to use my right thumb to fight that change towards me with my thumb pointed down, which means that all the induced things are going to be directed clockwise. We're now going to derive equations for all of these things. Let's put those dimensions back in there. There. All right, magnetic flux. Magnetic flux is essentially B times A. We know what B is. The area of this loop is X times L. So I think B X times L. That's the magnetic flux. What about the induced EMF? We just want the magnitude here. Lenz's law would have a negative sign there, but we're not worried about that for right now. We want to use Faraday's law, which says that the magnitude of the induced EMF is the time rate of change of the magnetic flux. Well, there's the magnetic flux. What's the time rate of change of that? Well, the time rate of change of position is v. There you go. What about the magnitude of the induced current? Current is voltage over resistance. BVL is the voltage, and the resistance of this circuit is given by R here. There's a resistor. We're assuming that the wire basically has zero resistance. I think we're going to get BVL over R. So far, so good. Electrical power consumed by the resistor. Well, let's see. What's power? The equation for power is I times V. We know what the equation for I is right here. BVL over R. BVL over R. And this is a capital V, right? Which is not the same thing as my lowercase v. This lowercase v is the speed. This capital V is a voltage, which is right here, BVL. So I think for power, you can just square all that stuff, can't you? BVL, whole thing squared, divided by R. And what about the force, assuming it wasn't given, that's required to maintain this constant velocity v? All right, well, that was an equation from mechanics a long time ago, but one of them was that the power was the force times the speed. And so if we want the force, we're going to have to take power and divide by v. So there's power right there. We need to divide that by v. So I think a v that is in here, there are two of them in the numerator. One of them is going to go away. So we're going to basically end up with something like this. The b is still going to be squared. The L is still going to be squared, but there's just going to be a v there divided by R. There you go. So those are the answers to all 5 of those posed questions right there.